Okay, thank you everyone. This is a very important occasion. We are about to witness the defense of the first student to come through the robotics PhD program. I want to give great thanks to the faculty who got together and wrote the document that allowed us to create a master's and PhD program. That happened in May 2013. I was at MIT at the time and not here doing the hard work. Art Quo locked Ella Atkins, Don Tilbury, Ryan Eustace, Ed Olson, and Ben Kuipers, I believe, in a room with a set of Google Docs and said, get to work. And they were led through the process, got some nice good drafts, and then we started the hard work of pushing things through Rackham, the College of Engineering. And when you create a graduate program in the state of Michigan, it has to go to something called the College of University Presidents at the state level to get it approved. That all got done in record time. So by January 2014, the graduate program was approved. We stole a few students from departments to get the thing going because we were way past the time to be recruiting them in any other manner. And that group included Josh Mangelson, Ross Hartley, Mia Stevens, and the young lady who spoke at our groundbreaking, Katie Skinner. So with that, I will let Ryan Eustace and Ron Bezudevan introduce Josh.
So this is one of the great parts of the job of being a faculty member is to get to come up here and to see one of your students really mature and kind of flourish and be ready for that next stage of their career. So I can remember when Josh came in like a starry-eyed kind of brand new grad student, didn't know really anything about kind of like marine robotics and everything that kind of goes and entails with that. I think what you'll find today in the thesis talk is that you'll see a really rigorous, very strong, mathematically kind of rich thesis, and really his co-advisor, Ron Bezudevan, has been really important, I think, in terms of helping to co-mentor and to kind of shepherd Josh through this. The one thing that's probably not going to come through, though, in this talk is that putting electronics in the ocean is a highly unnatural act. And so the experimental side of what kind of goes into the success that you see here, it comes down to inspecting 3-cent O-rings and looking for nicks in them and knowing how to kind of put the right amount of lubrication on it and that kind of stuff, so that when you put these robots in the ocean, really, that you have the opportunity to kind of do this rich experimentation and get the data back. And so Josh has spent many weeks bobbing up and down in a boat off the coast of San Diego, looking at the hulls of big ships, doing this kind of autonomous ship inspection. So I guess Josh got a bug for wanting to kind of keep staying in marine robotics and keep chugging along. So it's really great to see that after he graduates at Michigan, he's actually going to go off and do a postdoc with Michael Kess at the Carnegie Mellon Robotics Institute for a year, also working in this area of marine robotics. And then he's also going to be accepting a faculty position at BYU in electrical and computer engineering, and wants to kind of continue to pursue working in marine robotics. So with that, Josh, I'd like to come up and tell us what you've been doing. Sure.
So I'd like to just thank my committee as well, and everyone here actually, because I've had a lot of people help over the last couple of years, and I've really enjoyed being here. So, okay, so one of the things I'm interested in doing is developing reliable autonomous systems that are able to perform real work in real world environments. So within the manufacturing domain, robotic systems have been able to lead to a huge difference over the last several years. So here we have a video of about 20 robotic systems that are all working in collaboration with one another in order to perform a manufacturing task. And within this domain, robotic systems have led to dramatic increases in efficiency, dramatic increases in safety, decreases in cost. But you can think of other situations where robotic systems could be able to make a huge difference as well. So if you think about moving teams of robotic systems such as this out into real world environments, they can have an even greater impact on our society. If you think just about our civil infrastructure, we have large man-made structures, such as dams, bridges, or piers, that are all in need of regular inspection. So the American Society of Civil Engineers estimates that we have 90,000 dams in the United States, and 17% of those have a high hazard potential. Same thing with bridges. We have 614,000 bridges, and 9% of those are structurally deficient. So in order to repair these differences, we need to be able to perform inspection of these structures. And the way that inspection currently is carried out is through the use of divers manually. And that could be time consuming, it could be expensive, and it can be dangerous for the divers in many cases. Sometimes it can take days even for them to cover these large structures. But you can think of a situation instead where you have a team of 10 robotic vehicles that are all working in collaboration with one another in order to automatically perform an inspection task such as this. And if you were able to do this, you could more regularly perform these inspections. You could also more quickly and at a cheaper cost perform these inspection tasks. And you could also provide quantitative results. So it's difficult for divers to be able to determine if they've actually covered the entire structure because they're just visually checking to see if as they swim around to be able to look at the structure. But you could build up a 3D model of these underwater environments if you have robotic systems. But we haven't seen robotic systems such as this be nearly as widely adopted as we have within this domain. And part of the reason is because within these unstructured domains, there are a set of problems that are hard to solve in a reliable manner. While within this domain, those problems are heavily simplified. So I want to talk about what some of those unique problems are that exist within these unstructured environments that don't necessarily exist within manufacturing. So one of those first problems is called localization and mapping. So localization and mapping corresponds to determining where a robotic system is in its environment, and also determining where the other robotic systems, if it's a multi-robot team, where they are in relation to each other. And within the manufacturing domain, this is a heavily simplified problem because the robotic systems are actually bolted into the ground. So we know exactly where they are in space. And they're able to measure with a high degree of accuracy where their arm is in space using encoders. But if you move out into unstructured environments such as an underwater domain, you need to be able to estimate where you are in space as you move and potentially build up a map of the environment that you're moving through. So here we have a video of this robotic vehicle that I've worked on for the past several years. It's performing an inspection task. So as it moves through the environment, it has to build up an estimate of where it's been. So this blue line represents its trajectory. And it's in order to estimate its trajectory, it's fusing measurements of its own motion, and then also taking measurements of the environment using cameras and sonar, and then correcting its estimate of its trajectory as it moves through the environment based on that camera. So as you see, when it passes an object it's seen before, you get this red line, and you can see that it corrects its estimate of trajectory. So this ability to estimate its trajectory as it moves through space needs to be done really reliably for a robotic system to be able to navigate in an unstructured environment. And the reason for that is because if you have a bad estimate of your trajectory, you could end up taking a vehicle that looks like this and making it look like this. So it's really important for us to be able to estimate where we are in space well, and also build up a map of our environment if we're going to have it. A second problem that's really important is that of perception. So perception corresponds to taking in data of your environment and then determining where objects are in your environment that you can then interact with. And in the manufacturing domain, that's also a heavily simplified problem, and they don't actually have to perform perception in many cases. And that's because the objects they interact with are on a line that moves them to an exact location with millimeter accuracy every single time. So it's just pre-programmed into these arms where to put the bolts. So they don't actually have to perform perception and determine where they are, where the systems are that they're working with, or the things in the environment that they interact with. But when you and I navigate in space, we use our sense of sight, our sense of hearing, potentially our sense of touch, in order to determine where we are in space and what objects are around us. And robotic systems have to do the same thing. So they use sensors such as camera or LiDAR, sonar when you're in the underwater environment, in order to perceive where you are in space and perceive what's around them. So here we have an example of two images that were taken by this robotic vehicle as it was performing an inspection task. And what it's trying to do is it's trying to match an image it's seen in the past to an image that it's currently seeing. And if it's able to make a match between those, then it can either use that information to correct its estimate of its trajectory or to identify an object in the environment that it's trying to interact with. But we run into complications and difficulties in this problem in this space because of the complexity of the environment that we live in. So there are often multiple locations in an environment that look very similar to another, especially if you're interacting with man-made structures. So here we have 3 images that were all taken from different locations on the shipple, but they all look very similar to one another. And if you were to match to an incorrect image, you could end up either drastically affecting your estimate of your trajectory or interacting with an object that wasn't the target object. So being able to handle outlier measurements is also an important problem when we're trying to solve these problems. But how are these problems solved currently? They're usually solved by using probabilistic graphical models in order to represent the uncertainty in the data that we're observing. And then we form an optimization problem on top of that to be able to estimate certain parameters, such as the trajectory of the robotic vehicle. And this works really well because it enables us to model the noise and the uncertainty, but there are specific cases where this may tend to fail. And as you can tell, these optimization problems tend to be quite complex optimization problems, and sometimes, for example, they may have multiple minima, and if we get caught in a local minima, then the system may output something that could cause a failure of the system, or lead to unsafety. So one of the things I'm interested in is reformulating these problems in a way where we can guarantee that we can find a globally optimal solution or avoid these reliability or robustness. So as Ryan mentioned, for the past couple of years, I've been working on a project where we have 2 robotic vehicles that we use to perform regular inspections of shipholes. So a couple times a year, we'll go out to San Diego, and we'll use these 2 different vehicles in order to perform an inspection task on these shipholes. And what we're trying to do is we're trying to split up the work between these agents so that we can more efficiently perform these inspection tasks. Because even with a robotic vehicle, for divers, it can take a day or 2 in order to perform an inspection task. For these robotic vehicles, sometimes it can take several hours. And so if we need to be able to inspect a shipple in a short amount of time, we want to be able to split that work between multiple vehicles in order to increase the efficiency. But in order to do that, we have to build up a map, have each vehicle build up a map of the shipple that they're inspecting, and then merge that into a single consistent map in real time in order to perform that. And there's been a lot of work that's looked at how do we perform, build up maps or perform navigation in this way. But the existing methods tend to have a certain set of failure cases. So my research is mainly focused at how do we solve some of those failure cases and resolve them in a way where we can more reliably and robustly perform these inspections. So to give you an outline of my presentation, first I want to talk a little bit about SLAM, or what are some of the state-of-the-art methods for solving navigation, and then what are some of those failure cases, and an overview of the contributions. Then I'm going to dive into a couple of a little bit of the details of each of these methods. Some of them will be much more higher level than others just because of time constraints. And then I'm going to talk a little bit at the end about future work and then also reliable autonomy in general. Okay. So the way that these robotic systems navigate in space and what the state-of-the-art methods that are used to solve these currently is called closed graph simultaneous localization and mapping. So what we do is we take a robotic vehicle and we take measurements of its environment as well as measurements of its motion as it moves through space, and use that to estimate our trajectory as well as to build up a map of the environment. So here we're going to have an example of a robotic vehicle shown by this blue triangle here. And then each of these stars represent locations or landmarks in the environment. So and then this blue ellipse represents the uncertainty of the robotic vehicle. So it represents how certain the vehicle is of its location. So it's 99% sure it falls within this space. So the first thing it does is it's able to observe objects in an environment, and then as it moves, it's able to measure its motion. So here the robotic vehicle is taking a step forward, and it's able to measure its motion, shown by this green line here. And you can tell that the uncertainty here is increased quite a bit. And the reason for that is because this measurement is uncertain. So it knows it approximately moved this much. But now if we're able to re-observe something that we've seen in the past, then we're able to shrink that uncertainty because we can use the information of what we've seen before. And as the robotic vehicle continues moving through space, it continues to add additional locations that it tries to estimate and observe more objects. But if it's able to re-observe something which we call a loop closure, then it's able to dramatically just shrink its estimate of its uncertainty. Okay, so this is the general idea, but the way that we really formulate these problems is using factor graphs and probabilistic graphical models. So I want to now step through this one more time and talk about the probabilistic graphical model that we use in order to represent these problems. So in a factor graph, there are two different types of nodes. So the first node is a variable node. So this x1 here corresponds to the position and orientation of the robotic vehicle at time step 1. And then we have a pretty good estimate of where we are in space. So this factor node represents a measurement, telling us about where we are at the beginning. As we step forward in space, we now want to find the position and orientation of the robotic vehicle at 2 different time steps. And we have now another factor that's derived from this measurement that tells us where, how these two variables should be related to each other, probabilistically. And then if we re-observe something we've seen before, that becomes another factor or measurement within this graph. So we can continue moving forward. And now we have a representation of the problem we want to solve. We have a set of positions of the robotic vehicle, denoted by x, and then a set of measurements that tell us how they're related to each other. And if we model the probability of each of these measurements, we can formulate this as the maximum likelihood estimation problem. So we want to find the set of positions that maximizes the likelihood of the measurements that we have. And if we make certain assumptions on, such as additive Gaussian noise and independent measurements, then we can formulate this as a weighted, nonlinear weighted least squares problem. So what we have here is a function f that predicts what our measurements should look like. So each of these individual measurements, we predict what they should look like based on our current estimate of our positions, and we try and minimize the error between what we predicted they should look like and what they actually were observed. And so there's been a lot of work that looks at how we can solve this efficiently, and how we can solve it quickly, and for large graphs, and develop the scalability of this problem. But there are several failure cases of this method. And so I want to talk about what some of those failure cases are. So the first failure case is when we have outlier measurements. So if we were to observe an object in space that turns out to be a different object than what we thought it was. So if we see this star here, but we actually think we see this star, then we're going to end up with an incorrect edge in this graph. And that corresponds to an incorrect term in our cost, and so we're going to drastically affect our estimate of our trajectory. So these methods tend to fail when you have outliers. They also tend to fail if you have a bad initial guess. So the optimization algorithms that are used to solve these are usually nonlinear optimization algorithms, and so they take the initial estimate and then find the closest local minima. And so if you get a bad initialization, then they'll get caught in local minima. And then they also tend to fail if we have an inaccurate estimate of our uncertainty after we've solved some. So we run into problems when after we solve some, we want to be able to use the information that we've estimated and know how well we have our estimate, how likely our estimates are to actually be true. And we need to be able to accurately characterize them. So towards these 3 failure cases, we've proposed 4 contributions within this thesis. So the first one is a method that was published in ICRA that talks about how we can take 2 robot maps that were generated in overlapping areas and a set of potential loop closures between them, and then merge them into a single consistent map. But while handling the fact that we may have a large number of outliers. The second one talks about how we can align trajectories with one another if we don't have a good initial estimate, and if we don't have high-dimensional data, so we can't uniquely identify positions we've seen. And that was published in Oceans. The third one is a way of framing the general SLAM, simultaneous localization and mapping problem, in a way where we can guarantee that we can find a globally optimal solution, even if we don't have a good initial solution. And that will appear in ICRA this year. And then we also have a paper that's under review for TRO that talks about how we can accurately characterize the uncertainty of poses as a robot after we've solved this problem. Okay, so now I'm going to jump into this first one here, and then we'll continue with the Okay, so as I mentioned before, especially for man-made structures, there are multiple locations in environment that look very similar. And as we see here, each of these images were taken at different locations on the shipple. But if you're actually over here, and you think that you've seen this object over here, when you try and estimate your trajectory, it's going to try and force those 2 locations to be nearby one another. which is going to affect your estimate of your trajectory. Show an example of this. This is a trajectory of a robotic vehicle as it moves through a building. Just by adding 2 outliers into this graph, it drastically affects our estimate of our trajectory. And things get even more complicated when you have multiple vehicles that are simultaneously trying to build up a map together. So here, each vehicle is estimating their own trajectory as they move through space. And then we have a set of potential loop closures or factor measurements that tell us how they should be related to one another. But 90% of these may be outliers, and we want to be able to determine which of these measurements we should trust. And so there has been quite a bit of work that's looked at how we can determine, handle these outliers when we have these different, when performing simultaneous localization. But they tend to fall into 2 groups. So the first group looks at the size of this residual error term, and if it's large, then they say that measurement must not be likely, and so they throw that measurement. But that's dependent on initialization. So it's dependent on what your current initial estimate is. There's also been methods that look at consistency. So they look at pairs of measurements or sets of measurements and try and measure their consistency. But they don't necessarily enforce that the entire group of measurements they select are consistent. So in this chapter, what we do is we formulate this as a combinatorial optimization problem that one doesn't require any initial guess and enables us to select a set of measurements while guaranteeing the set of measurements we select are pairwise consistent with each other. And then we talk about how we can transform that into an equivalent problem to increase the efficiency. Okay, so to formalize this a little bit more, we have a set of measurements Z that represent potential measurements that relate the 2 graphs that we're trying to merge. And we want to find a subset of those measurements Z tilde, where the subset of those measurements we can trust. And the way we're going to do that is by looking at pairs of measurements and checking how consistent they are with one another, and then trying to find the largest set of measurements that are all consistent with each other. So we have a set of measurements Z. We want to find the subset Z tilde, and we specifically want to find the largest subset Z tilde, where we're constraining every pair of measurements within Z tilde to be consistent with one another. And this consistency metric really depends on the type of measurements you have as you move through, and the type of measurements you're observing. But what we're going to use is what's called the all-notice distance. And so it enables us to take into account uncertainty when we're determining how likely these measurements are.
Josh, how big is this set typically that we're talking about here?
Yeah, so for us, we're able to handle several 200 or so measurements. But it depends. When you're in a single robot case, you may have more than that. So it really depends on the problem you're trying to solve. But for us, when we're trying to merge 2 robot maps, to a couple hundred is good enough. And so as Justin was alluding to a little bit, this is a combinatorial optimization problem, so it's hard to solve efficiently. And so what we're going to do is transform it into an instance of the maximum clique problem, and so that we can leverage existing literature in order to apply existing algorithms to solve it more efficiently. So the way we do this is we look at pairwise consistency of every possible pair of measurements. And we build up a consistency matrix, which tells us how likely each measurement is to be consistent with each other. We then convert that to a consistency graph by thresholding this matrix. And so now in this consistency graph, each node represents a measurement, and each edge denotes consistency between those measurements. So now finding the largest possible pairwise consistent set corresponds to finding the maximum clique of this graph. So we can apply any of the existing algorithms from graph theory in order to find the maximum clique. And then once we have this maximum clique, we now just merge these 2 graphs with one another using just the measurements that are. So from an evaluation standpoint, we've evaluated this using both simulated and real-world data. So in the simulated environment, we took an existing data set, split it in half, generate both inlier and outlier loop closures between the 2 graphs, and then generate 200 synthetic worlds in that way. And then we also took an existing data set that was collected here on North Campus using this Segway robot, and as it moved through the environment, we took, it was created as it moved through this environment, but then we took that existing data, 2 runs of it, and generated inlier and outlier loop closures using the LiDAR data that was So to give you an idea of the color scheme here, we've got two trajectories for two robotic vehicles shown in blue and green. And then we're going to show false positives in red, false negatives in pink, and true negatives in gray. So you want to have gray, you don't want to have any red or pink. So if you use the existing methods that enforce that use the residual error in order to determine which measurements should be trusted, if they're given a bad initialization, it disables all of those measurements. Methods that look at consistency, such as single cluster graph partitioning or ransack, don't necessarily enforce pairwise consistency every single time. So they can lead to inconsistent graphs. While our method guarantees a set of measurements it's selecting are pairwise. In addition, both ransack and pairwise consistency maximization have this threshold parameter that has to be set. But if we're using Mulholland nodal statistics, then it's a chi-square distribution, and so we can set it a priori beforehand. And our method is much more robust to the tuning of that parameter because we're looking at pairwise, a group-wise consistency as opposed to individual. So if we vary that threshold, then our method is much less effective than ransack.
So that one leads to the big chunk out of the.
Yes. Yeah, that one leads to the
Okay.
sun robot. Turns up 3 weeks later.
Yes.
Okay, so from a quantitative perspective, we also outperform each of these other methods in terms of translation and rotation mean squared error when trying to align these graphs. So in conclusion on this chapter, we've developed a method that doesn't require any initialization, and it guarantees the set of measurements it's selecting are pairwise consistent. We've talked a little bit about how you can increase efficiency of that, and we've released the code at this link if anyone's interested in that. Okay, so now we're going to move on to this next one. This one, we're going to be a little bit higher level just because of time. But the idea here is that in some cases you don't have enough data, you either don't have the sensors or you don't have the communication in order to directly match an object that you've seen in the environment for one vehicle to an object you've seen that the other vehicle has also seen. So you may want to be able to align trajectories based on just some underlying feature, which could be curvature of an object nearby, such as a ship hull, or it could be bathymetry of the seafloor. And what we want to be able to do is align this query trajectory with the reference trajectory. So we're assuming that two robotic vehicles have moved through the space. They've measured this feature space as they move through the environment. And we want to align this trajectory with this one. But we want to do it in a way where we don't have any initial guess. So we don't want to assume that we have an initial termination. So in order to do this, this kind of gets broken into 2 steps. So one, we need to develop a convex cost function so that we can determine how to align trajectories with one another without any initial guess. And so the way we do that is we take points within this query trajectory, we determine their distance in feature space to every point within the reference trajectory. And then we use that to build up a point cloud that tells us how points within this space relate to their dissimilarity with points. And then by taking the lower convex hull of that point cloud, we now have a linear cost function, which tells us where points in this space should align in this space. And then by summing that cost, we get a linear cost that tells us how this should be aligned. And so now it's a convex cost function. The second part is once we have this cost function, we need to enforce that the trajectory we're estimating is actual rigid body transformation. And the special orthogonal set of matrices or special orthogonal group is not it's not convex. So we run into problems there as well. So the way we get around that is we use an L2 norm approximation, so a linear approximation of the L2 norm, in order to enforce that the rotation we're estimating is approximately. So now we have a way of using a linear program in order to align these trajectories with one another with an approximately. So just to conclude on this section, we've developed a method that enables us to align trajectories with one another that based solely on a low-dimensional feature set. It doesn't require any data association and it doesn't require any initialization. And then we've also released the code for this method. Okay, so now I'm going to move on to this next section. Does anyone have questions about that last section? So what we want to be able to do in this section is determine a way where we can formulate the SLAM problem, so such that we can guarantee we can find a globally optimal solution every single time without having any prerequisite or conditions on our initial estimate for the problem. And so as we talked about before, this is the cost function of the optimization problem that's often used in order to solve the simultaneous localization and mapping problem. And this F function is often very nonlinear. So this results in a cost function that has multiple minima. And so what we want to find the maximum likelihood estimate, or the true estimate of our trajectory, is find a globally optimal solution. But if we're given an initialization that isn't within the basin of attraction of the actual true global optimal, the way these algorithms work is they descend to the closest local minima. And so we're actually going to end up finding a different solution than the actual estimate of our trajectory. And this is important again because we're using this to do navigation. So the true solution, or the globally optimal solution, should be our estimate of our trajectory in space. And if we get caught in a local minima, we're either modifying our estimate of the world, or we're ending up with a trajectory that doesn't actually represent where we are. So from a safety perspective, we run into problems. So there's been recent work over the past couple of years that's looked at how can we resolve this problem of getting caught in local minima. So the first couple methods looked at how do we relax the optimization problem to a similar optimization problem that isn't the actual original problem, but it's one that's convex, so that we can find a globally optimal solution, and then they reinitialize the nonlinear optimization using that initial guide. But there's no guarantee that you're finding the globally optimal solution. Other works have looked at using Lagrangian duality in order to verify if you have the true solution once you've already found an initial guess. And most recently, there was a work that looked at under certain noise assumptions, can we guarantee that we can find the globally optimal solution? That was SEC, it was published by David Rose. But none of these methods actually formulate the optimization as a convex optimization every single time. So what I want to be able to do is guarantee we can find the globally optimal solution regardless of noise assumptions, and really formulate it as a convex optimization. So what we're going to do here is we formulate the planar SLAM problem as a polynomial optimization, and then we guarantee that we can find the globally optimal solution to this polynomial optimization problem, regardless of initialization. Okay, so in order to do that, we have to talk a little bit about how these poses are represented. So the way that these positions of the robotic vehicle are typically represented is using a vector of parameters. So this is the robotic vehicle's position and orientation at time step I. And that's often represented using translation parameters and then angles, which represent in 3D the Euler angles. So it describes our orientations. And then every single pose is also represented in that way. And in this case, we're going to assume that our measurements are also full degree of freedom transformation, so they also follow the same structure. Well, we run into problems because the angle here, this angle parameter, is not actually a real number. It falls on a manifold. So things get a little bit more complicated. And when we're subtracting our estimate of our measurement from what our actually observed measurement was, if the angles are both near 0 or 2 pi or multiples thereof, then we run into problems when we're trying to do the subtraction. So what we want to do here is actually represent our orientation using SO2. So the traditional way of representing poses is shown here. But what we want to do is actually use rotation matrices and translation vectors in our costs. And more specifically, we want to be able to represent our parameters as real numbers in that space. So we have CI, SI, XI, and YI. But in order to ensure that this is a valid rotation matrix, then we have to enforce that CI and SI lie on the unit circle. So enforcing this constraint makes this be a valid rotation matrix. But then we have, as we perform the optimization, we have to enforce this non-convex constraint. The nice thing about this, though, is since we're using real numbers here, we can, when we measure the distance between two different angles, it actually doesn't matter if we wrap around or not, because we're measuring that distance in the equivalent of XY. Okay, so what we do is we take this new representation and then we reformulate the optimization problem as a maximum likelihood estimation problem, but using this other representation for pose. So here now our poses that we're trying to estimate are R and T. Those are rotation matrices and translation vectors, where we're enforcing that this matrix, which lies in the real 2x2 matrices, follows this constraint. And then we also represent our measurements in that way. So while this cost looks a little bit more complicated, it's actually doing the exact same thing as in the previous formulation. So this term is just measuring distance in rotation, and this is just measuring distance in position. So we're trying to take our existing measurements, predict what our pose has to be in order to minimize the error. And once we have this formulation, we can now plug in those rotation and translation vectors, rotation matrices and translation vectors, and we get a polynomial cost function. So now we have a cost function that's trying to estimate parameters c, s, x, and y that are real numbers, with a polynomial cost and these quadratic constraints. So what we were able to do in this paper was prove that this cost follows a very specific structure. And so we can guarantee we can find its globally optimal solution by solving a convex semi-different program. And so now by solving the semi-different program, we can always find the globally optimal solution to this polynomial cost maximum likelihood estimation problem without having any initial guess of our estimate every single time. And so to experimentally validate this, we took existing data sets, split them into parts because the method doesn't scale currently as it currently is. Well, we have ideas of how that can be done, but as it currently stands, it doesn't quite scale. We took a random initialization and initialized some of the nonlinear optimization methods, and they get caught in local minima, while our method is able to find a globally optimal solution, and it doesn't need any initial guess. From a quantitative perspective, we also took those same data sets and split them up into chunks, and we outperformed those the nonlinear solvers in those cases as well. So from a conclusion on this section, what we're doing is we formulate the planar post-scratch slam and landmark slam problem as polynomial optimization problems, and then we are able to prove that we can find a globally optimal solution every single time. Any questions on?
Could you talk about the implications that it doesn't scale and yet you can downsample a data set and still have a global, the optimal solution to the downsampled? How would you use that in the bigger?
Yeah, so I think there's two answers to that. So one is you can take existing larger data sets and break them down into equivalent smaller data sets, right? Which that is one way of trying to solve that problem. But you can also, we have some ideas on how you can scale this algorithm. So the structure of the SLAM problem is sparse, and so there's the sparsity of the problem that you can leverage. But in addition to that, that sparsity also means that you can kind of break the problem up into smaller pieces. So that and then guarantee you can find the globally optimal solution later on as well. So that's something we're currently working on.
Okay, that'll be your future work.
Yeah.
Okay.
Has any prior work done the same sort of simplification of using the C, S, and C, and then forcing that constraint on it, and just not solved it in a guaranteed optimal way?
Yeah. So there have been some methods that they formulated as a quadratically constrained quadratic program, and they do solve it, but they are relaxing the problem in a slightly different. So they're not necessarily. So that some of the initial methods I mentioned that were solving the problem, a relaxed version of the problem to a global minimum, then using that as initialization for another problem, for the nonlinear solver. You are doing something like that, where they're enforcing something similar to what we're doing.
So in the cost function you showed, you had an unlabeled norm on the translation rotation.
Yes.
But does it not matter to this context, or you pick them?
So I was mainly showing that just to show the main overview. The norm is dependent on the measurement model. So you're measuring, you have some estimate of the noise parameters for your measurement model, and that ties into what norm you're using. So often we use Mahalo-Nova systems, which is a norm that scales everything by the inverse of the covariance. But you can also, when we're talking about the rotation matrices that I was checking there, I think it's using Probabilistic or a weighted version. But yeah, so usually you use that weighting dependent on how certain you are of your measurements being correct. So that does draw from the specific.
When you say scaling, like how big pose graph are you typically solving this style?
Oh yeah. So these experiments here were, I can't remember exactly. I think they were like 20 to 30 to 20 to 50 nodes or so. This problem here is like 400. But this takes about a minute or so to solve. So there are ways of increasing the scalability of it, but we're currently. Any? Yes.
So when you say it doesn't scale, is it just the amount of time it takes to solve, or is it?
Yeah. Yes. Yeah. So it's the amount of time it takes to solve, and then also memory can also tie into it as well.
Does this scale at all to 3D?
Yes. So actually, a paper was published or put on archive 3 days ago that extends our method to 3D in some portion. It's only doing rotation, and it doesn't really solve the entire problem. And for them, they can only handle 10 nodes. But there are methods that are trying to look at that as well, and we're also interested. Any other questions? Okay, so now I want to move on to this last computation here. So as we mentioned before, after we solve the simultaneous localization and mapping problem, we extract our current solution, but we also need to be able to have a good estimate of how well we know where the robotic vehicle is. So if you think about a self-driving car that's driving down the road, it needs to have an estimate of where it is in the lane, but it also needs to know how well it knows that estimate. So if it's really certain of its estimate, then it can use that in order to navigate. If it's uncertain, or if its estimate is not correct, but it thinks it's certain, it may end up crossing into the other lane, right? So it's important to be able to determine a good estimate of your uncertainty as well, as opposed to just finding the solution. And so Smith, Self, and Cheeseman published a paper in 1990 that talked about how you can represent pose and represent uncertainty of your pose specifically. So the way they do this is they use this vector of parameters, and then they model that as being a multivariate Gaussian kind of variable. So by using this covariance, by modeling in this way, they can use this covariance matrix to track how well they know their estimate of their uncertainty. In addition to that, they talked about if you have multiple poses, you can stack those and then model that as a larger jointly multivariate Gaussian random variable. And then they talk about how you can perform pose composition, pose inverse, and relative pose operations on that data. So how do you propagate uncertainty through composing poses, inverting a pose, or finding the relative pose between two existing poses while modeling that uncertainty. And this is really important, or being able to model that jointly correlated nature of these poses is important because after you solve SLAM, all of these pairs of poses are correlated to one another because your estimates of them are derived from the same measurements. So here we have an existing SLAM solution where we've extracted pairs of poses that are offset from each other by 50 nodes, and these are colored by correlation. So the black is a coefficient of 1, and white is a coefficient of 0. So the majority of these poses are correlated in some way, and a lot of them are very highly. And this is really nice because it enables us to model that uncertainty, but it doesn't necessarily really show. It's not able to accurately characterize the uncertainty of real poses in the real world. And the reason for that is because if you have a rotation error early on in your trajectory, then you're more likely to end up out here than you are to end up in the middle in here. And so when you're enforcing a multivariate Gaussian random variable over these parameters in XY space, you're not able to actually use this Gaussian representation to represent the rest of your pose, or accurately model what this uncertainty looks like. So Tim Barfoot in 2014 published a paper that looks at how you can represent this pose uncertainty in a more accurate. So the way he does this is he uses the Lie group structure and the Lie algebra of the special Euclidean group in order to represent this uncertainty. So he represents a pose using a mean, which is actually in the group, and then he uses a random multivariate Gaussian that's translated to the algebra of the group, and then translated to the used to perturb the mean value through the exponential function. So there's a random variable that's defined in the Lie algebra, and then we perturb our mean variable in the group by transforming that through the exponential. So the nice thing about this exponential function is it handles the nonlinearity of the alpha function. Yes.
So R6 is the evaluating?
Yes. Yeah. So it's R6. Well, that's the dimension. Yeah. So if you think about it in 3D back on this representation, it would actually be X, Y, Z, and then RPH or some other combination of other angles. And within the Lie algebra, you have the same. Okay. And the nice thing about this is it enables you to directly characterize that puzzle uncertainty. So shown in green here is using this parameterization of uncertainty to accurately map what the actual sample puzzle is uncertainty. Okay, in addition to that, Tim Barfoot also talked about if you have independent poses. So if you have two poses that are modeled in the same way, you can propagate uncertainty through the post-composition method or operation by using the equations here, which uses the adjoint of the transformation. But he does assume that the poses are independent. So in order to summarize this, Smith, Self, and Cheeseman developed a method that enables you to represent pose uncertainty using a set of coordinate vectors, or a vector of coordinates, but that doesn't necessarily enable you to accurately characterize pose uncertainty. They also talk about how you can handle jointly correlated poses and then derive the pose composition, pose inverse, and relative pose operations. Tim Barfoot talks about how you can use the algebra, which enables you to better characterize that uncertainty, but he assumes that poses are independent and he only looks at the pose composition operation. So in this chapter, what we're going to do is develop a framework for handling jointly correlated poses in the Lie algebra, and then derive the first order uncertainty propagation methods for pose composition, pose inverse, and relative pose based on that. And then we also release a C++ library implementation of them. So let's talk about how we characterize the jointly correlated poses. We're going to use the same model as what Tim Barfoot has here. So we have a mean vector that's in the group, or a mean matrix that's in the group. And then we have a multivariate Gaussian noise or perturbation parameter that's in the Lie algebra. And then we transform that through the exponential function to perturb our mean. And what the difference here between what Tim Barfoot does and what we do is he assumes that these are independent, while we stack these uncertainty perturbation vectors and model them as being a jointly Gaussian. And by then using the BCH function or the Baker-Campbell-Hausdorff equation, we can derive the post composition, post inverse, and relative pose operations based on this method. And we're able to take into account correlation, which wasn't taken into account before. Okay, so when we perform experiments, we can show that ignoring that correlation leads to an over/underconfidence. So if we're assuming positive correlation, then when you do post composition, you under-approximate uncertainty to ignore correlation. And when you do relative pose, you over-approximate uncertainty. So ours is shown in green, and then blue is if you ignore the correlation. In this case here, we also perform two different experiments to be able to evaluate this. So the first experiment, we generated a trajectory of transformations. We sampled the uncertainty of each consecutive pose to be correlated with one before it. And then we generated 10,000 samples of those trajectories, and then compared it to what what our method as well as SSC or the independent linear algebra method use to determine how many of the samples fall within our uncertainty bounds. So all of the methods drop off as you increase the number of steps in your trajectory, but our method is much more accurate than each of the other existing methods. And the same thing when we increase the noise level. So if we increase rotation noise, our method also outperforms. In this case, when you have translation noise, SSC does get to about the same as us, but the main reason for that is because the nonlinearities are being derived from the rotation error, right? So it doesn't, as you increase your translation error, it doesn't necessarily affect, our method doesn't necessarily do any better than what SSC would do, because you're just adding XYZ in a straightforward way. And for the second experiment, we took an existing SLAM data set, we extracted two pairs of relative poses from that data set, and then used Monte Carlo to derive what the true distribution of the relative pose operation should look like, and then compared our method to SSC in that case. So here, zero error is white, and dark orange is higher. So here we're outperforming SSC in each of these methods. So we were outperforming the Smith-Selton-Cheesman method by an order of magnitude. So to summarize on this section, we've developed a method that enables us to use the Lie algebra to jointly characterize pose uncertainty, and then we derived the first order uncertainty propagation methods or formulas for the pose composition, pose inverse, and relative pose operation. And then we've also released an open source C++ library. Any questions on this section? Yeah.
So you're still dropping off the number of steps.
Yes.
Is that because you're using a local linearization?
No, so we're not using a local linearization for our method. Well, you could term it as a linearization, but we're using what's called the BCH formula. So the BCH formula is it describes when you multiply rotations in a group space. How does the addition how does that affect your Lie algebra terms? And we're associating uncertainty in the Lie algebra, so we're dropping off the higher order terms there. So as you add more and more nodes, you're going to increase in error.
So it's not approximation that you're losing.
Yes, so it's in the higher order terms approximation. Okay. The dropping off. But there's actually kind of surprising this slide here to think about composing 30 poses in your SSC method doesn't even work anymore, which is something we've used for a long time. So, any other questions on this section? Okay. All right. So now I want to move on to conclusion. As I mentioned before, we've had four main contributions. So one's a contribution that looks at how do we represent or handle outlier measurements when we're trying to merge maps, generated multiple. Second one looks at how do we align trajectories with one another if we don't have a good initialization and we don't have high dimensional data, so we can't uniquely identify positions. The third one talks about how we can formulate the SLAM problem or the planar SLAM problem in a globally optimal way, so we can guarantee we find the globally optimal solution. And then the last one talks about how we can, after we've solved SLAM, how can we accurately represent pose uncertainty so that we can increase the safety. From a future work perspective, both the globally optimal SLAM formulation as well as the first chapter where we're talking about how we can represent outliers or determine which measurements we should trust. Both of those are currently using full degree of freedom constraints or full degree of freedom. And so both of those have methods that could be used in order to extend them to more general types of measurements, such as range-only measurements, which you often have in the underwater environment, or binocular image registration. Also, we can increase the reliability of these systems, or the real-time capability of these systems. Specifically, as we talked about before, the globally optimal SLAM, there's ways we can extend that or make it more scalable. In addition, when you talk about reliable autonomy, we've talked about some of the methods, the problems that exist in this space that are hard to solve reliably and consistently in this space. But being able to robustly perform those tasks is only really a part of reliable autonomy. So when I think of reliable autonomy, I think of four main elements. So there's algorithmic robustness, which is what I've been talking about so far. There's also constraint management, system cognizance, and system operator cooperability. And I think each of these tie into developing systems that are reliable. So in order to talk about those a little bit more, I'm going to use the same motivation here, because one of the things I'm interested in is developing a system of 5 or 6 robotic vehicles to automatically perform inspection tasks. But when you talk about algorithmic robustness, again, it's talking about navigation or even planning. How do you develop these algorithms in a way where they will reliably give a true solution? Constraint management, though, there's also the system that you've developed or that you're using, as well as the domain that you're operating in, often enforces constraints on the operation of your system. So when you're talking about the underwater environment, we often have heavily limited communications within this domain, and so being able to have a team of robots coordinate with one another well is dependent on them being able to operate under those limited. In addition, the algorithms that we're developing here also have to be able to run in real time. So there's interesting things where you look at, can we develop these algorithms in a way where we can guarantee that they'll be able to run in real time every single time? When you talk about system cognizance, you can increase the reliability of these systems if they're able to be aware of themselves and also the task that they're trying to perform. And if they're able to replan based on that awareness. So if you think about a task that you're given to a robotic system, and each individual team, or you're given to a robotic team, and each individual system has its own capabilities. If the system's aware of the capabilities of the individuals, as well as the of the task that it's trying to perform, it should be able to dynamically plan which vehicles do what in order to increase the reliability of the system. And from a similar perspective on an individual system level, you want each system to be reliable or be able to handle failure cases within its own system. So if you think about a robotic system that has multiple sensors, you think of one sensor being used for target tracking, one being used for obstacle detection, and one being used for path planning. But if one of those sensors were to fail, you would want the system to be able to determine that failure has occurred and start using other data in order to continue operating, especially if the robotic vehicle is down or underwater for weeks or months. So there's interesting problems to look at. How can the system be aware of itself as well as the task it's trying to perform and continue operating to increase reliability? And then also the communication between individual vehicles with each other, as well as between the system and the operator, is also an important part. So when you're talking about reliable autonomy, if you think about how well an operator is going to trust the system to actually perform a task, it's important that the communication between the operator be able to handle potentially vague instructions or high-level instructions. And as I've been using this underwater perspective in order to motivate things, but all these same topics apply to each of these other application domains as well. So in conclusion, I just want to thank my collaborators as well as the members of my committee for all of their time and help. And then I'd be happy to take any questions people have.